Hello, everyone. Welcome to our Deep Dive podcast, where we review the latest and most impactful research papers in AI. Today, we're exploring a fascinating paper titled Spatial Reasoning with Vision Language Models in Ego-Centric Multi-View Scenes. Are you ready to get started?
Absolutely. This paper is from a team at Huawei Technologies Canada and Huawei Cloud, and it addresses a crucial challenge in AI: understanding 3D spatial relationships using vision language models, or VLMs, in real-world, ego-centric, multi-view environments. That's a mouthful, but it's a really important topic for robotics and autonomous vehicles.
Right. Let's start by clarifying what egocentric multi-view means. In this context, egocentric refers to the perspective of an agent, like a robot or a self-driving car, moving through the world, capturing images from multiple cameras pointing in different directions. This is different from just having a single camera or a static surveillance setup.
Exactly. And the multi-view part means that the agent is getting simultaneous images from several viewpoints, front, back, sides, and so on. This setup is much closer to how humans perceive their surroundings, integrating information from both eyes and turning their heads to build a mental map of the environment.
The paper points out that most previous benchmarks for spatial reasoning in VLMs have focused on single images or videos from static, indoor scenes. But real-world agents need to reason about space dynamically as they move through complex outdoor environments. That's where this new benchmark, Ego3D-Bench, comes in.
Yes, Ego3D-Bench is the first benchmark specifically designed to evaluate the 3D spatial reasoning abilities of VLMs using ego-centric, multi-view outdoor data. It's built from over 8,600 question-answer pairs, carefully curated from three major public datasets: New Scenes, Waymo Open Dataset, and Argoverse 1.
That's a huge effort. And the questions are not just random, they're designed to require true 3D spatial understanding. For example, a question might ask, how far is the red car in the left view from the blue truck in the front view? The model has to integrate information from multiple images and reason about their spatial relationships.
Exactly. And to ensure quality and diversity, human annotators played a central role in both constructing the dataset and reviewing the questions and answers. This helps make sure the benchmark is both challenging and reliable.
Now, the authors benchmarked 16 state-of-the-art VLMs on Ego3D-Bench, including big names like GPT-4o, Gemini 1.5 Pro, Intern VL3, and Qwen 2.5-VL. What did they find?
The results are quite revealing. There's a significant gap between human performance and the best VLMs. Humans can naturally integrate information from multiple views and build a coherent mental map, but current VLMs struggle with this kind of spatial reasoning.
That's a key insight. The paper hypothesizes that the main limitation is the VLM's inability to construct a unified world model from multi-view images. Humans do this effortlessly, but VLMs need some help.
To address this, the authors propose a new post-training framework called Ego3D-VLM. The core idea is to generate a cognitive map based on estimated global 3D coordinates of objects mentioned in the input prompt. This map is then provided to the VLM as additional context.
Let's break down how Ego3D-VLM works. First, it uses a referring expression comprehension (ROC) model to find the 2D locations of objects in each camera view. Then, it uses a depth estimator to predict how far away each object is.
Right. Next, it projects these 2D points into 3D camera coordinates using the camera's intrinsic parameters. Then, it transforms all these points into a global coordinate system, usually centered on the front camera. This simulates how humans use a consistent frame of reference as they move.
After that, the system scales the 3D points using known object sizes, like assuming a person is about 1.7 meters tall, to make the spatial relationships physically plausible. Finally, it generates a textual cognitive map that describes the positions of all relevant objects in 3D space.
This cognitive map is then fed to the VLM, along with the original images and the natural language query. the VLM uses both the structured spatial information from the map and the rich visual cues from the images to answer the question.
The results are impressive. Across all model sizes and tasks, Ego3D VLM provides significant improvements on average. A 12% boost in accuracy for multi-choice questions and a 56% reduction in error for absolute distance estimation.
That's a big deal. It shows that providing structured spatial representations helps VLMs reason more effectively about 3D relationships, especially in complex, dynamic environments.
Let's talk about the types of questions in Ego3D-Bench. There are 5 main categories: absolute distance measurement, relative distance measurement, localization, motion reasoning, and travel time estimation. Each category has both ego-centric and object-centric variants.
For example, absolute distance measurement might ask, how far is the ego from the red car in the right view? Relative distance measurement could ask, which is closer to the ego, the blue truck in the front view or the pedestrian in the left view?
Localization questions are object-centric. They ask the model to infer the location of one object from the perspective of another. Motion reasoning questions ask whether moving in a certain direction will bring the ego or an object closer to or farther from another object.
And travel time questions ask, given a certain speed, how long would it take to move from the ego's position to the location of another object?
These are all tasks that require integrating information across multiple views and reasoning about 3D space. The evaluation metrics are mostly accuracy for multi-choice questions and root mean squared error, RMSE in meters, for absolute distance estimation. The benchmark also includes human performance as a reference point.
Interestingly, humans are very good at relative spatial reasoning but less accurate at estimating exact distances, especially in object-centric scenarios. This highlights the challenge of the task.
The paper also compares Ego3D VLM to other approaches, like models that use point clouds or bird's-eye view images. These methods can be accurate, but are computationally expensive and hard to use in dynamic, real-world environments.
Ego3D VLM, on the other hand, is modular and efficient. It only focuses on the objects mentioned in the prompt, which keeps the number of input tokens small and enables fast reasoning.
The authors also conducted extensive ablation studies to understand the contribution of each component. For example, they tested different formats for the cognitive map: visual, JSON, and textual. The textual and JSON formats performed best.
They also tested the impact of using estimated versus ground truth camera parameters and object lists. Even with estimated parameters, the cognitive map significantly boosted performance. Using ground truth information provided an upper bound, showing the potential of the approach.
Another interesting experiment involved feeding the cognitive map to a text-only language model, without any visual input. The results were worse than with a full VLM, but still better than chance, showing that the structured map carries a lot of useful information.
The paper also benchmarks Ego3D VLM on other multi-view datasets, like All-Angle Bench and VSI-Bench. Even though these datasets have different setups, Ego3D VLM still outperforms the baselines, demonstrating its adaptability.
Let's discuss some limitations. The performance of Ego3D VLM depends on the quality of the underlying VLM and the external tools for object detection and depth estimation. If these components are weak, the overall performance suffers.
That's true. The paper notes that for models with limited reasoning ability, like VLA 1.5-8b, Ego3D VLM provides little to no improvement. Also, the depth estimation in outdoor environments is still a challenge, and the relational scaling approach is only an approximation.
The authors suggest that future work should focus on fine-tuning VLMs with ego-centric multi-view data and incorporating 3D projection modules directly into the training process. Improving depth estimation and integrating better spatial reasoning are also important directions.
Before we wrap up, let's summarize the main contributions of the paper. First, Ego3D-Bench is the first benchmark for evaluating 3D spatial reasoning in VLMs using ego-centric, multi-view outdoor data. Second, Ego3D VLM is a plug-and-play framework that enhances spatial understanding by generating cognitive maps. Third, the experiments show significant improvements across a wide range of models and tasks.
This work is a big step toward building AI agents that can understand and navigate the real world as effectively as humans. It highlights the importance of structured spatial representations and sets a new standard for evaluating and improving VLMs.
I agree, the gap between human and model performance is still significant, but Ego3D VLM shows that we can make meaningful progress by combining vision, language, and structured spatial reasoning.
That's a great note to end on. Thanks for joining us for this in-depth review of spatial reasoning with vision-language models in ego-centric multiview scenes. We hope you found it informative and inspiring.
If you enjoyed this episode, don't forget to subscribe and check out our other paper reviews. Until next time, keep exploring the frontiers of AI.
To summarize, this paper introduced Ego3D-Bench, a new benchmark for 3D spatial reasoning in ego-centric multiview scenes, and proposed Ego3D-VLM, a post-training framework that significantly improves the spatial understanding of vision-language models, bringing us closer to human-level performance in real-world environments.